Hello and welcome. In our previous lessons, we mastered deployment. We now know how to run application, scale it up to multiple replicas, and manage its lifecycle. But this creates a new problem. With multiple pods that can be created, destroyed, and replaced anytime, how do users or application reliably connect to them? This is where the service objects come. A service is complementary concepts to a deployment. While a deployment manages running a set of pods, like replicas, a service is responsible for exposing those pods as a single stable network endpoint and routing traffic to them. While you can use this concept in isolation, they are designed to be used together. This combination is what gives you a truly scalable and resilient application. The deployment handles the scaling, and the service provides the stable address and load balancing for all scaled replicas. Every service you create must have a type. This type determines how the service is exposed and where it can be reached. And for most use cases, you need a master for primary types. First is ClusterIP. This is default type. It exposes the service on cluster internal IP address. This means that the service is only reachable from within the cluster. This is perfect for backend services like database or API that don't need to expose to the public internet. Second is NodePort. This is exposes the service to the static port on each node IP address. This is static port is chosen from high numbered range, typically from 30000 to 32767. This is allow you to access the services from outside of the cluster by hitting any NodePort IP address and then NodePort. And the third, load balancer. This is the most advanced type. It exposes the service externally using cloud provider load balancer. When you create a service of this type in a cloud environment like AWS, Azure, or GCP, Kubernetes will automatically provision a cloud load balancer for you, giving you single stable and public IP address. In this course, we are using MetalLB for creating the load balancer, which we will talk about it later. ExternalName is a special type of Kubernetes service that doesn't create a proxy or IP inside the cluster. Instead, it maps a service name to Kubernetes to external name. When pod uses the service Kubernetes, return a CNAME record pointing to the external DNS. The most important thing to understand about service is that it uses labels, selectors to find pod to send traffic to. Let's see how to create one for those examples. We will use this simple Nginx image. I'm switching to my terminal. The most important thing to understand about the service is that it uses labels, selectors to find a pod to send traffic to. Let's see how to create one. For this example, we will use simple Nginx image. First, let's create a pod. The kubectl run command automatically assigns a run Nginx label, which is perfect for our demo. First, let's create a pod. The kubectl run command automatically assigns a run equal Nginx label, which is perfect for our demo. So copy the kubectl run command. And as you can see, it's run Nginx with image Nginx using port 80 and restart never. So I'm creating the pod. Now that we have a pod with label, we can create a service to select it. We will use kubectl create service. We have to provide the type. In this case, ClusterIP and the port mapping using TCP flag. This says expose port 80 on the service and route traffic to target port 8080 on the pod. So before exposing the service, let's look at the pod itself, describing the pod. So we have Nginx here. Okay, describe pod Nginx. And as you can see here on the labels, we have run equal Nginx. This is important for exposing the service. So now I'm gonna use kubectl expose command to create the service for this Nginx pod. kubectl is smart enough to see that our service is named nginx and will automatically create a label selector for run equal nginx, matching the pod we just created. Let me just create this. Okay. Now we have nginx servers here. And if I describe this service, you can see to selectors is selecting run equal nginx. Now we can have access to service via curl. So I'm using my Ubuntu image, which is already running in the namespace. And I'm using curl nginx to see how it does. As you can see, I can get the nginx response from the nginx pod, from the nginx service. So the second method is production ready. In the real world, you are not running single pods. You are running deployments. The recommended workflow is to create your deployment first and then expose the deployment itself. So I'm going to use kubectl create deployment nginx, and the image is nginx and replica is 2. Okay, in the Ubuntu, so I'll execute it here. So if we get the pods, you can see we have these 2 pods created. So now we use the kubectl expose deployment command. This will read the labels from the deployment and create service for the correct selector. So let me copy the thing. So I'm going to use expose deployment nginx port 80 target port 8, and I will name this service nginx-deploy. So it's exposed kget pods, and you can see in services we have nginx deploy. If I describe this service, we have this label selector app equal nginx. This is different from run equal nginx. This means that this is a deployment. So app equal nginx is exposed with the nginx deploy service. So let me use again the curl. So I'm connecting to Ubuntu again, and I'm using curl nginx deploy. And as you can see, now we have this nginx HTML response. So this is the cleanest and most common way to create a service for your application. Of course, all of these imperative commands are just shortcut for creating YAML manifest. Declaratively, a service look like this. So let me show you the YAML manifest. I'll use YAML file like svc.yaml. I already have this here, but I'm removing this. So as you can see, the kind is service, the metadata name is nginx, the type is ClusterIP, and selector is run equal nginx. So if I remove the already existing nginx, like k delete svc nginx, and then k apply svc nginx svc k apply -fsvc.yaml. This will create the same service for us. So this is the recommended way to creating the service. You can see all of the key pieces. The type, ClusterIP, and the selector is for run nginx, and the maps that own port 80 to container target port. So how does this all works? Let's investigate. If we list our services, we get a high level overview. Okay, get svc. So now we have nginx and nginx deploy. We see our services, its cluster IP and its port. But how does it know where sends the traffic? This is the most critical concepts to understand. A service does this not send traffic directly to the pod. Instead, it sends traffic to the endpoints. An endpoint is a separate object that Kubernetes creates and manages for you. These endpoint objects watch the cluster for any pods that matches the services selector and are in ready state. It then builds a list of IP addresses and ports. The services simply read this list. We can see this by describing our services. So I'm using kubectl describe svc nginx deploy. And here under the endpoint section, you can see that we have two endpoints for our service. Look at the endpoint line. It has found two of our Nginx pod from the deployment. If we scale our deployment up to the 10 pods, the endpoint object will update to the 10 IP address. If we scale it down to 1, it will update it with 1 IP. The service just reads this list and load balance traffic across them. This separation is the key to troubleshooting. If your service isn't working, always check the endpoint slices. If the endpoint slices list is empty, it means your service selector doesn't match the labels on your pod. Let's make a service without existing pod. So I'm using hello world service. This is a YAML definition. Okay, as you can see, the service name is hello world, and I'm using the selector run equal hello world, which doesn't exist in my cluster. So I'm going to apply this, and I'm getting the service. As you can see, hello world is empty if I'm describing the hello world. As you can see here on the endpoint, it's empty, it's null. So we don't have any endpoints to pointing to this service. Another way to getting the endpoint slices is to getting directly the endpoint slices discovery kubectl. So here hello world is port is unset and endpoint is unset, which means that it couldn't find any endpoint with this specific label. The final piece in this puzzle is a port mapping. It's simple but trips many people up. Port is a port that service itself listen to inside the cluster. In our example, this port is 80. Target port, this is the port that your container is listening on inside the pod. In our example, this is like 80 again, because the Nginx is listening to 80. So let's change the service port. Right now we have get svc. They have this Nginx deploy service. So I'm editing this service and changing the port to the 8080. The target port remains 80. The target port means it's pointing to the current running container inside our pod, which is listening to the 80 port. But 8080 is something that exposed internally in our cluster. So let me changing the service. Now, if I go to the Ubuntu image again, Ubuntu pod again, and curling this, you can see that it's unable to connect to the port 80 because we have changed the service. So if I pointing to the 8080 port here, you can see we get the result. This means that port is for internal and target port is for the container. Traffic flows like client, service, and then to the pod. Let's test each our 4 service types. ClusterIP. As we said, ClusterIP is only reachable from within the cluster. I'll create an Nginx pod and I'll expose it with ClusterIP service in port 5005. I'm using kubectl run command to create my pod Nginx here. Get pods. So the Nginx pod is running. Now it's time to create a service for this pod. And I'm using this. So I'm pointing the port 5005 to port 80 in the container. So the service is also created. And as you can see, the service now has this address as a cluster IP. If I curl the cluster IP here on the node, you can see it gives us the result on port 5005. And this is perfectly predictable because we are inside the cluster at the moment. So kubeproxy is creating the virtual IP for us. So then we can access to this IP address. But if I'm going out of the cluster, let's say here, and then curling the endpoint on port 5005 on my local machine, you can see that this is unreachable because we are not inside the cluster. So this is the expected behavior. Now let's try to access from the inside the cluster. Let's say running a Alpine curl image. So I'm going to connect again to the pod, and now I'm using Alpine curl image and name it my shell. I'm using TTY. Okay, now I'm inside the container. So I'm using this curl and this, and I'm instead of this IP address, I'm using the current pod IP address, which I was selecting like 10. Yeah, as you can see inside of the pod, we can also connect to this service. That's cluster IP internal access only. So NodePort. Now let's create a NodePort service. This will gives us the cluster IP, but also open a high numbered port on every node in the cluster. Before getting access to the NodePort, we'll describe the Nginx NP. As we said before, the endpoint, when the endpoint is empty, it means that there is no endpoint for this service. We can find the result because it's looking for app equal Nginx NP, and there is not any Nginx NP app at the moment running in our cluster. To fix the issue, I'm going to use kedit svc Nginx NP, and then I will replace this label selector with the Nginx. So then we will have service which is pointing to the Nginx, but right now the app Nginx is not running. To create the deployment, I'm using kubectl create deployment Nginx, image Nginx, and replica 2. This will create a replica set for us, and then we can use this service. So if I'm describing the service again, we can see that this service now has 3 backend pods, 2 from the deployment and 1 from the basically the pods that we created. Right now, if I'm getting the services, we can see this service is exposing on this local port IP address and this port number, which is 32743. So if I get the nodes -o wide and see the internal IP address, our internal IP address for our node is this. So I can curl this node and then pointing to the port, which was 32743, and you can see that we can get the pod. And we can do it also in my computer because I have the route to this machine. So if I'm doing this, you can see still I can get this information from my cluster. So it's exposed to our environment. As you can see, we can access the exposed node port from both machines, so it doesn't matter where is you or port actually running. The kubeproxy is handling the routing and forward the traffic to the node that has the backend pod. Finally, the load balancer type. This is for cloud providers. But in self-hosted environment, you can use MetalLB to have a similar capability. MetalLB operates in 2 modes. The first one is simple layer 2 based load balancing, and the second one is operating in BGP, which is beyond this course. Let's start with MetalLB with Helm. So here in the controller, I already have the Helm. So I'm adding the repo. So it's here. To updating the repos, we can use Helm repo update, and this will update the all existing repos. And then I'm using helm install metal-lb, and I'm using metal-lb, and I'm installing in metal-lb system namespace, and I will create a namespace. This is necessary because this namespace is not there, so this will create a namespace for us. And then configure the metal-lb to use layer 2 configuration for service advertisement in our cluster. So what I'm going to do is using a chunk of IP address in my local area network, which is, let me show you the information. I already have this here. So the range is 192.168.2.0 and /192.168.2 /.250. It means that this can choose IP address from this range. Basically, what it does is it using ARP, and then it's discover that any available IP address in this range. So whenever I'm creating a new, let's say, load balancer, it's looking within this range to find a new IP address for the load balancer. Let's demonstrate this so we can see if the metal will be running in our cluster. So all of the pods are running, speakers and the controller. So for each node that we have running in our cluster, metal will be creating a speaker. So in this way, if one of the speaker dies or just disappear from the cluster, other speakers can expose the load balancer service to their system. Okay, now it's time to applying this manifest. So I've created this manifest. Now create a load balancer service pointing to our application. I'm using a YAML definition, LB YAML, which has the name of Nginx LB, and the selector is app Nginx, which is pointing to both of deployment and the pods running in our cluster. So I'm going to apply this manifest using apply-f the LB YAML. So this will create a SVC or service for us, and the service address is 192.168.2.1 from within the range that we defined for our metal LB. Now, when we got the services, look at the external IP column. The cloud provider has provisioned external IP for us. In this case, the metal LB. I can access the IP directly on the service port, not the node port. So here I can use curl and connecting the port 80 on here. As you can see, we can access this on the same machine or on the control plane node, or also we can access it from my local machine. So I can use this, and you can see that we can access to this machine. It's different from the ClusterIP or from the NodePort, because here this is available for us. If I had a public IP address, you could have access from within the internet. This is the beauty of load balancer. Now, before we move on to the other hands-on demos, there are one special service types we need to cover: external name. This type is completely different from the other three. External name service, it does not select any pod. It doesn't have selector. It doesn't get cluster IP, and it doesn't manage by endpoint. So what does it do? It acts as a DNS alias, specialist CNAME record, within your cluster. Its entire purpose is map your internal service name to external public DNS name. Let's look at quick example. xname.yaml. And I'm using this external DB, and I'm pointing it to the API simpleapis.com. So if we get this, before applying the change, I want to check the existence of this name in the cluster. So I'm going to check that if we have any record for this. So I'm going to use exec, and then here I'll use nslookup and check the, as you can see, we're getting the NX domain because this domain doesn't exist. But let's go and apply this change. So I'm going to apply the x name YAML. So now if we get the services, you can see that we have this external name type here, and it's pointing to the external IP, which is API simpleapis.com. So if I exec again to Ubuntu Bash and nslookup now you can see that we have multiple IP addresses and we have this CNAME API simpleapis.com here. With this service created, if any pods inside of my cluster try to connect to the IP address my external DB, the cluster internal DNS will do something very simple. It will see this external name service and reply with it, I can't give you an IP for that, but its real name is something like this. The Pod DNS resolver will then go and look for the IP addresses for the API simpleapis.com. Why this is so useful? It allows you to decouple your in-cluster application from the external services. Your application can be configured to always talk to the stable internal name, like my external DB, if your external database address ever change. So this is a rare case that your database name changed, but maybe in some use cases that can be helpful. You only have to update this one external name service. You don't have to reconfigure and redeploy every single application that connects to it. It's a simple but powerful tool for service discovery when dealing with the resources that live outside of your Kubernetes cluster. So let's recap. Service provides a stable network endpoint for shifting set of pods. They use label selectors to find their target pods, and the result of that search are stored in the endpoint object. ClusterIP is for internal only communication. NodePort exposes your application on a port on every node, and LoadBalancer integrate with your cloud provider or MetalLB to give you a dedicated external IP. Understanding how to create, inspect, and troubleshoot services is fundamental skill for every Kubernetes administrator. Thank you for watching, and I will see you in next topic.